下最后1个小时，大家忍耐一下，可以忍耐一下。almost over. So let's get started. Okay. So remember, when we went through the syllabus, I told you this course, okay, linear algebra primarily is about matrix manipulation, right? So what is matrix? Don't expect I give you full here on the red here. 你们都不知道，你们都太年轻了，有没有看过那个 matrix 的电影 ？Keanu Reeves 那个红药丸，对啊，没事，对，就是 matrix，OK， 不是那个把你们当做电池的，对，it's not the movie star， matrix this is matrix， okay， so basically previously I just shown you, okay, I've just shown you a system of linear equations, right? So you have seen all those coefficients, right? So you can actually write those coefficients into a matrix, okay? So if you do that, then remember we have n number of linear equations in our system of linear equations, right? And we have n variables. So, if you write the coefficient, those aij into matrix, then we will have n rows, okay, where each row is, 就是在中文我们叫那个列，就是横的。It's a for example, this A1 from A1 to about A1 represent the first row, A21, A22, about A2, A2 represent the second row. Okay, and so on. So we have n rows. Each row has n numbers or n coefficients. Okay, and we will have n columns. Okay, n columns. Okay, column is, if you look at this matrix in vertical shape, then each vertical, this vertical stuff is column. So for example, A1 from A21 to AN1 is first column, and A12, A22 from AN2 is the second column, and so on. And we will have n columns, and each column we will have n numbers there. Okay, so this is a matrix. We call such a matrix as n times n matrix. Okay, so the first number represents the number of rows. The second number represents the number of columns. Okay. So if n times n matrix means we have n rows, n columns. Okay. So come back to how to identify Chinese and Taiwanese. Okay. If you see a Chinese and you can ask them, okay, about matrix, and if they say, okay, if they say, okay, row for Taiwanese. 我们 row 是讲那个列，我们的 column 是讲行。For Chinese, for people from China, they use these two terms exactly opposite. Okay, 他们的列是这样子，他们的行是这样子。OK， 是颠倒的，就是我们的在台湾，我们的行列跟他们的行列用法是颠倒的。So this is one way to identify people from China. If you do not want to use, Taiwanese to identify people from China, 你不用说你不要跟他说，哎，你骂个我骂看看，这样子，那你用这个，这比较文雅，对吧？这个开玩笑，好。So after you understand that, you can represent a system linear equation by a matrix. Okay, for example, this system. Okay, first of course you need to line up the variables, and then you can write their coefficient into matrix like this. This is coefficient matrix. Okay, coefficient matrix like this. And if you want to include those constant, you want to include the constant, okay, on the right hand side in the matrix, then this matrix, okay, you will have one additional column. It's called augmented matrix. Okay, so the only difference between coefficient matrix and augmented matrix is that you have one in augmented matrix, you have one additional column that comes from the right hand side of this system linear equations. Okay? And then with this augmented matrix, okay, you can do those row operations just like how we discussed earlier, okay, including multiply a row by a non-zero constant, add the multiple of a row to another row, and interchange two rows. These three operations. And these three operations, if we are in matrix discussion, we call them this operation as elementary row operations. Elementary row operations. Okay. So so here is an example. Okay. This one obviously represent augmented matrix, right? Okay, this one is exactly this one, right? Okay, and then we just use like elementary row operation. Okay, the first one we exchange like row 1 with row 2. So this is notation R1, R2. That's the notation, but I don't care about that. Okay, to be honest. Okay, you just need to know. Okay, what are row elementary row operation, but as for like these notations, I don't emphasize. I'm trying not to emphasize on memorizing stuff. Okay, in my class, I care more about understanding than to memorizing stuff because I'm poor at memorizing stuff. If I'm good at something, I will test you on those things. If I'm poor at something, I don't think it's fair to ask you guys to do better than mine. Okay, so basically, this notation, obviously it's easy to understand, but I will not ask you to remember how to write them. But you need to know this exchange two rows is obviously one of the elementary row operations. And this is like you multiply row 1 by -2 and add two rows and put it in row 1. So that's what happens. And this the third one is the third elementary row operation. You multiply row 1 by -2 and add to row 3. Okay, and put it in the row 3. So at the end it's from left hand side to right hand side. Okay, should be very easy to understand. Okay. So we can also discuss the row echelon form in matrix. Okay. Matrix is in row echelon form. Okay. All rows consisting entirely of zeros must occur at the bottom of the matrix. Remember, row echelon form is the steps. It's like 像梯子一样，对不对？既然它全部是零嘛，那你就可以缩到最后面，对不对？所以 all those zeros, okay, if all rows are zero, they must appear, at the bottom, obviously, right? So for each row that does not consist entirely of zeros, the first non-zero entry is 1. That's the leading one, right? That's exactly the same as like how we talk about row echelon form for the system linear equation. So for two successive rows, the leading one in the higher row is further to the left than the leading one in the lower row. 就是上面一层的，它的那个 leading one 会比较左边，就是这些都很好理解。这个就是那个 stepwise 那个这样子往里面说嘛。So every column that has a leading one has zeros in every position except the leading one. Okay. 就是在这个有一个 leading one，OK， 如果说你就只有一个 leading one， 其他都不是其他都是零。那这样子的我们叫 reduced row echelon form， 就是它比 row echelon form 再更近。OK， 就是全部那整行都是零。或者说你如果讲到说那个 system linear equation， 那就是它已经是比如说 x 等于多少 ，x1 等于多少 ，x2 等于多少，这样子，已经是那样子的形式。So let's have a look. Okay. So this is from the top one. This is obviously non-row echelon. So we represent this one by augmenting the matrix. And then, from the top one, okay, we multiply the first row by, we add the first row to the second row, okay, and multiply the first row by -2 and add to the third row. Okay, so by doing so, the second row and third row, the first position for both become 0. And then we have the leading one here, right? So here, okay, we can, add the second row to the third one to try to carry up this -1. So we have this one. So this is already reduced, so already row echelon form, okay? We've already a row echelon. Oh, sorry, not yet. And this one is not leading one. The leading coefficient is not 1 yet. So we need to modify this row by 1/2. So yeah, so this is row echelon form. Okay, and then we just backwards substitution. So this is the same. Not much. But you can practice this one. Okay, try to practice this one. I will give you like some do it. Okay, and obviously like the first row, you don't have x here, so then you have to do a stretch. Okay, to put like for example the second row into the first row. Okay, you can stretch the first row, second row, and then continue doing. Okay, should be doing it right. Now the practice is. 可以吗？So here's the solution. You will find like when the dimension is increased, it takes more time because obviously just your solution. I mean, of course, here it must be the same, but you may have different process because I was talking about you can do exchange, do exchange between the first row and second row. You can obviously also do exchange between first row and fourth row, right? It's really up to you. So there are more than one choices, but eventually you must come down to one and the only correct answer here. Okay. So now you know how to do a row echelon form. So remember we discussed the number of solutions. So if you have an inconsistent system, then you are going to end up with a row with zeros, except for the last entry. Okay? So, in other words, here, of course, I'm talking about augmented matrix. So, in other words, all the xi, their coefficient are zero. But on the right-hand side, the constant is non-zero. It's impossible, right? It's impossible. 左边是零，右边是不是零？ It's obviously impossible. So if you are going to encounter such a situation, you are going to this system is going to be inconsistent. Okay. So if you do not encounter such a situation, then you must have a consistent system. I mean, for consistent system, there are two cases. One is exactly one solution. Second, you have infinite number of solutions, right? So for one solution case, okay, the number of non-zero rows is equal to number of variables. If that's the case, we have exactly one solution. For infinite solutions, okay, the number of non-zero rows is less than the number of variables. Okay? So this is how we identify the number of solutions. Okay. So one thing, okay, that we can think about, if the system of linear equation is homogeneous, what do we mean by a system of linear equation is homogeneous? That means all the constants on the right-hand side are zero. Okay, 所有右边的那个 constants 都是零。OK， 左边当然那个 x1、x2 那边，它的 coefficient 是可以是零的，但是右边那边都是零，这个叫做 homogeneous system。OK， if it's like that, then it must be consistent, right? It must be consistent because it's no matter how you use the elementary rule operation, because the right hand side is already zeros, right? So it is impossible for you to come up with a non-zero on the right hand side, right? So this inconsistent system situation never appears, right? It's not going to occur, right? So if it's a homogeneous system, only discussion comes down to whether or not you have one solution or infinite solution. Okay? So, yeah. In which each of the constant terms is 0 are consistent. So only discussion is like if you have one solution or infinite solution. If you have only one solution, then that only solution must be all 0. Right? Because if you put x1, x2, xn all to be 0, obviously it is one solution, right? If you have more than one solution, then it must be infinite number of solutions, right? We have discussed that already, right? Okay, so homogeneous system, okay. First, it must be consistent, okay. Second, if it has one solution, it must be all 0. Okay. If you have any non-all 0 solution, then you have infinite number of solutions for homogeneous system. Okay? So previously we talked about Gaussian elimination, right? So now we can talk about Gauss-Jordan elimination. Okay. Gauss-Jordan elimination. Okay. 这个 Jordan 不是那个打篮球的。对。So obviously, because you see Gauss, right? So obviously the Gaussian elimination is part of this. Okay, so we first convert this one to low echelon form. So it's like here. And then, okay, we can we can try to get rid of like a top non-zero terms. So first we add like -3. We multiply -3 to the last row, and then add to the first one, the second one, to cancel out these two. And then after we do that, we multiply the second row by 2 and add to the first row, so to cancel out this -2. So we get this one. This one is more of a reduced low echelon form. Okay? Reduced low echelon form. So the leading coefficient is 1. And other than that, like all the other are 0. Okay. Well, of course, not including this constant. Okay. Another example is here. Okay. So from this one, okay, I think this is the example we just practiced, right? This is the example we just practiced, right? So I think we get to this point. And then from here, okay, we can, get rid of the top non-zero terms, okay, from the bottom. So multiply this row by 1, add to here, to cancel out this -1. Multiply this row by 2, add to the second row, get rid of -2. So it becomes like this. And then we multiply this row by -1, add to here. Multiply this row by 1, add to here. So it becomes this. Last one, multiply this row by -2. Once you have this, obviously x is -1, y is 2, z is 1, and w is 3. So we can get the answer directly. No backward substitution is necessary anymore. Okay, but I don't know, of course, which one you want to take, to solve the system linear equation, it's up to you. But here, I just want you to understand this by the matrix multiplication. nevertheless, all these operations are still elementary law operations, right? They are still elementary law operations. And one more example. Okay, so from here, okay, I think that I will leave this one to you, okay, to practice. Okay, eventually, okay, one thing interesting is that, okay, eventually this one, after you convert this one to, reduce to row echelon form, you will find that, okay, the lowest row is all 0. Okay, and you have 3 rows that have leading 1. But you have 4 variables, right? So for a case like this, remember that tells you that you have infinite number of solutions. Okay? Right. Here, infinite solution. The number of non-zero rows is less than the number of variables. Okay? So the previous one is number of non-zero rows equal to number of variables. And this one is number of non-zero rows is less than number of solutions, number of variables. Okay? You have 3 non-zero rows, but you have more than 3 variables. Okay? So yeah, you can continue, okay, for this leading 1, you can multiply 1 enter here, multiply negative 1 enter here, cancel out these 2. And for this one, like multiply this row by negative 2, cancel these 2, okay, enter here, cancel out this 1. So eventually it become like this. So what happens is that, okay, look at here. It means like z minus w equal to negative 2. So in other words, okay, z equal to negative 2 plus w. Okay, and if you name w as t as a parameter, then z will be